Okay. Now I have to speak in a less of a loud voice. Okay. Anyway, so the two most basic tools in Fourier analysis are Fourier series, which they work for like periodic functions, and they were, say, invented by Joseph Fourier in hopes of solving the heat equation. And its shape is basically, you give a function, you can compute a series that approximates the function in L2. And this is basically a way of saying that if you integrate the difference of one function and the function and the series, it's going to be small, right? And I will introduce LP spaces in the following slide. And then we have the Fourier transform, which can be seen in three different ways. In mathematics, it's a transformation that's deeply rooted in the structure of our RD, right? As an abelian group. And then in physics, you have this meaning that, you can think of it as a probability distribution, like density, sorry. And it tells you what the probability of finding a particle with certain momentum in certain point is. And then in engineering, it's the amplitude of a frequency. So if you have, I'll explain it now. Well, let's go into LP spaces and then into the Fourier transform. LP spaces, basically, for those who have not seen measure theory, is imagine you have a set, right? And you put a measure on it. So that's basically a way of measuring subsets. So, for example, on RD, you have the Lebesgue measure, which is basically the area. So in R1, it's lengths. In R2, it's areas. And in R3, it's volumes. And that's a measure, and you have a measure space, which is RD with the Lebesgue measure. And so LP of RD is the set of functions which are integrable. The absolute value of the function is integral to the power p. And you have this norm, and when p is infinity, well, you have this other norm. But like basically, if the function is bounded, anyway. And LP spaces have some interesting things, right? So they're normed vector spaces, meaning that they're vector spaces, and you can measure length. And L2 is a Hilbert space, so you have an inner product. So you can multiply, let's say, functions with a weird non-pointwise product. And in RD, these functions decay somewhat nicely, because otherwise they would integrate infinity, no? An infinite amount. And these LP spaces interact through interpolation, meaning that if a function is in LP and it is in LQ at the same time, then it's in LR for every R that's in between P and Q. So they let's say, interact nicely. And then you have some operations that are very natural in LP. So the first one is the convolution. This is basically, we will see that this is a way of looking at a function through another function, but we can postpone that. But yeah, basically this is like one of the most important operations, and it's commutative and satisfies this, meaning that, so if f and g are functions that integrate a finite amount in absolute value, then the convolution also integrates a finite amount. There are translations as well, which basically is just like moving a function by a fixed vector. And there are modulations, which are an interesting operation in signal analysis, and well, they have this weird expression, but it all becomes clear in this graph. No? So if we have a bump function g, a translation would just move it. This is in R1, but in RD, it's just like moving it along the vector x. And then modulations, well, you can look at the real part of the modulation of g, and it's like, multiplying it by this wave thing, and it's nice to look at. And then if you combine a translation with a modulation, you get what's called a frequency shift. And frequency shifts are really important operators, like in time frequency analysis. But anyway, let's go back to the Fourier transform. So this is the formula, which again you don't have to remember. But basically, in signal analysis, what happens is that if you look at a frequency omega, right, the Fourier transform of f at omega tells you the amplitude that the function f, or the signal f, accumulates at the frequency omega. So for example, if you have a constant sound, which has a constant frequency, which will be determined by a wave, like the signal will be a wave, in this particular case, you will very easily see which one is the main amplitude frequency of this signal. But if you take it to Fourier space, let's say, so if you compute the Fourier transform, you will get a peak near this frequency, and the rest will be more or less flat. So mathematically speaking, it has some interesting basic properties. For example, it decays at infinity. This makes sense. So in this context, because if you have a signal, no, and you have a set of frequencies that are like the main frequency bands that dominate in this signal, then if you look further away, you will find nothing, because like it won't have like frequencies all the way up to infinity. It doesn't make sense. And then it has some also like nice properties, analytical properties, like it interchanges regularity with decay. So the more regular the function is, like the more derivatives you can take, the faster the Fourier transform decays. And it interchanges convolution and multiplication. So the Fourier transform of the convolution is the multiplication of the Fourier transforms. And then you have the way that it interacts with translations and modulations, which is by changing them. So like whenever you have a modulation, you have a translation in Fourier and the other way around. And these modulations and translations commute via this certain identity. So for integer x and omega, these guys commute, because the e to the minus thing is 1. And this is one expression that pops up in time frequency analysis a lot, and you don't have to remember it, but it's something that happens, no? Yeah, so L1 is nice. Like the Fourier transform is defined in L1, so that it makes sense. But the nicer space is L2, because we already said that it's a Hilbert space, and in Hilbert spaces you can do a lot more things than in L1. So the idea now is that we may be able to define a Fourier transform in L2, right? And how do we do this? Well, it's done through density of Schwarz functions in L2. Basically, you cannot come to a formula that gives you the Fourier transform of a function in L2. But what you can do is find arbitrarily close good functions that have a formula for their Fourier transform, and they just define it as a limit. And this is a very like useful and really popular technique in analysis and many other areas. So Schwarz functions are basically functions that decay really, really, really fast, like faster than any polynomial. This is what the definition is. And in L2, we have some good properties, like Plancher's theorem, which tells you that if you take the Fourier transform like in L2, it's an isometry. So you end up with something that's the same as what you came from. And you can measure distances, and distances are preserved. And yeah. And so basically, what you can do with this is, since you depart from the same set as the one you arrived to, and it preserves distances, it's injective and it's surjective, so you can invert Fourier transforms, right? So if you have a function in L2, you can invert it. So basically, another thing that you can do is go to like take a signal, Fourier transform it, modify it, and then bring it back to like bring back a modified signal of like that's going to be similar to what you started from, but it will have some other properties depending on what you like to modify. Anyway, this is an example of a Fourier transform. So that signal is called the Shepard tone. We will see it later in the talk, and this is what its Fourier transform looks like. I mean, this is like really condensed, right? It's like a wave that goes really fast, so that's why you don't see a function. You see like a graph, like a 2D graph, but it's really is just 1D. And what this is telling you is that this signal has overall its length, it has these dominating frequency bands. So it has a bit of all, except from that. But I mean, it decays, no? So that's obvious. So now the main point comes of what is really time frequency analysis. So think about it. You have a way to get frequencies from a signal, but you have to know the whole signal beforehand, because it's defined as an integral, and you integrate over the whole space, and you integrate the function over the whole space. So it doesn't really make sense to analyze signals this way, because if you have a song, for example, and you want to analyze the dominating frequency bands at some point, like close to some instant, you're going to have to weigh over all the signals, so you're going to lose a lot of information. So is there some way that we can do this? That we can maybe analyze what's happening near a point with the frequencies? And yeah, so these are the problems that I just mentioned, because this is motivated as well by the fact that if you're listening to a song, then you can sometimes instantly recognize what the key is or what the tone should be. Anyway, yeah, and signals vary with time. So what we need is what I said, like an instantaneous frequency spectrum at any time that we want. It's like a sheet music, no? So you have in music you have time that goes on the horizontal axis, and on the vertical axis you have the notes, and these represent frequencies. So if you have this, you can build the function, the signal. But we want to do something that's like maybe bring back this process. No? So you have the signal, you want the sheet music. So the most intuitive idea or the most naive idea would be to take the function or the signal that you're looking at in like close to a point x in time, and take the Fourier transform. So you take delta here and small, and then you compute the Fourier transform of f times this characteristic function. But there is a problem with that, and it comes in the form of uncertainty principle. So basically, if you do that, you're screwed. That's what it says. Uncertain principles tell you that you cannot really localize in time and in frequency at the same time. They tell you that if your function is, like, if you know what your function looks like really well in time, and you want to compute the Fourier transform over a small interval, frequencies will go wild. So this is the first uncertainty principle. This is the Heisenberg uncertainty principle. So you can think of this as probability distribution. So if f, the absolute value of f squared, is the probability density of a particle being at some point, then the physics tell you that the Fourier transform is the same with the momentum, right? So this would mean that the product of the variances is bounded below. So if one is small, the other is big, and vice versa. So the probability that you find, so if you know really well that your particle has to be in a really small set, then the probability that you can find its momentum in a really big set is high. So you cannot really know both at the same time, right? And with frequencies, it's this similar thing, but with the time frequency, sorry, the time resolution and frequency resolution. But this is maybe better explained in the Donohue-Stark uncertainty principle, which tells you that, so for a function to be concentrated, epsilon concentrated in a set, it means that its L2 norm is really big in that set. So in its complement, it's really small. So it integrates like epsilon times the norm, the L2 norm, right? Which is this is what we call the energy of the function, and this would be the energy over this set, right? So what it's telling you, this theorem, is that if your function is really concentrated on a set t in time, then in frequency, its Fourier transform will be concentrated in a, so I said small, and on a big set. And you have this bound on the product of the volumes of the sets, right? So basically, if this is small and this is small, this is going to be big. I said that right, yeah? Yeah. Anyway. Or one of the two is going to be big. And so if we apply this theorem to the situation that we had before, what you find is that if you want your function to be delta concentrated on, so yeah, in time, so the time resolution to be really big, and then you want the frequency resolution to be very, very big as well. So let's say you can look at the function, the Fourier transform, and they give you a lot of information, then you're going to have a bound on the support of your frequency, like the set of frequencies that you have, right? And if you let delta go to 0 and mu go to 0, then that thing blows up. So it's going to be bad, basically. Or in terms that a boomer would understand better, if you use instantaneous frequency spectrum on these functions, it will fail every time. So we have a sad Pikachu. And so this is where the idea of the short-time Fourier transform is born, right? So the idea is that you have to take a function g with which you're going to look at f, and it has a support that's big enough for you to not be super concerned about uncertainty, and you can slide this function over the whole RD, right? RD, and for every point in space, you're gonna be able to find this instantaneous frequency spectrum, but it's not gonna be instantaneous. It's gonna be, you cannot do so well, no? But yeah, that's the idea. So what you end up with is a 2D representation of the function, yeah, in the what we call the time frequency plane. So at a certain time and at certain frequency, it will this short time Fourier transform will give you the amplitude of that frequency at that point in time, roughly. And there's a really neat way of visualizing this, which is spectrograms. So spectrograms basically are like the modulo square of the short time Fourier transform. And for example, in the film Arrival by Denis Villeneuve, which is a really good film, you should watch it if you haven't. You can hear some aliens speaking, and at some point they show a short time Fourier transform. And I have prepared some examples so that we all enjoy them together. Yes. All right. Okay, so that's a scale. And so you can see here that there's time and frequency, and these are the, let's say, dominating frequency bands at any point, right? Anytime you have a musical instrument that, for example, a string, so yeah, let's just focus on string, and you make it vibrate, it will vibrate at some frequency, but also one half of the length frequency. Anyway, these are called harmonics, and what I want to convey basically is that if you play an instrument, it's going to be more than one frequency playing at the same time, even though you may only hit one note, right? So this is what we see. We see the frequencies that dominate and their harmonics. This is going to happen. Like every time you look at a spectrum, it's gonna be a bit chaotic, but you can only focus, like you can focus only on one and think that the same is, like the rest of them are gonna be copies of this. And we have the function on the top, so the signal on the top, and then you have the spectrogram. This is what happens when, okay, now what we're gonna see now is what happens when you change the window. So far, I didn't say anything, but the window that you use, the function g, can be changed. And depending on the size of the support, it will give you better time resolution or frequency resolution. So this would be somewhat nice time resolution. I mean, well, it's a middle point, no? But if you take better frequency resolution, you see that you start to not know when each sound begins and ends, but the frequency bands get smaller and smaller. So you know which frequencies sound better, and like you have more knowledge about that. And then you can take this to the extreme, in which you don't know anything about the time resolution, but the frequency bands are really clear. And then I'll show you when it goes back, yeah. So contrast that before with this really nice time resolution that we have here. And you see that this is like the uncertainty principles in a picture. So yeah, let's see now what a music sheet in a spectrogram would look like, right? This is some Bach. Oh, well, this is another scale, and then it's going to be some Bach. This has more harmonics because it's a piano, not a guitar. So yeah. Okay, so well, I assume that everybody knows how to read a music sheet, but is really maybe not so clear. So basically, I should have said this earlier. The high frequencies are the ones that are on top, and then mid-range, and then bottom range or low range. And when the sounds seem like they go up, in like when you hear them, they go up in the spectrogram, and they go down similarly, and the idea is really clear. This is some Chopin, and you can clearly see here so here's gonna be like. Wait for that. That's gonna be awesome. Okay, so that's more like a really distinguishable piece of music. So what would a song that's more current look like? Well, you can see here. So you can see basically like the percussion, like when you hit the drums, you can see that a wide column, right? And then the waves in Rick Astley's voice, mesmerizing. Yeah. So basically, yeah, you have a lot of information with the spectrogram, and that's basically that's how Shazam works, right? And if you've ever wondered about this, it samples the song using your phone's microphone, then it computes the spectrogram, and then it compares in a database what it looks like with the spectrograms in the database, right? And then if there's a positive match, then it will give you back the song that has that spectrogram. So this would be basically the steps. Yes, it will always give you back All-Star. And well, let's forget about spectrograms now and go back to the Fourier transform. So these are some properties that it has, right? So these are the two most important ones. Basically, taking Fourier transform of the function f and the function g gives you a 90-degree rotation in the time-frequency plane. This is what the first identity means. And the second one just tells you that doing a time-frequency shift of the signal, so moving it, it's like moving it in the time-frequency plane, and up to some factor over there. And then it also satisfies some nice properties that are similar to those of the Fourier transform. So it satisfies some orthogonality properties. And these yield a sort of like Parseval formula or Plancherel formula. So what you get is that it takes L2 into L2 of R2D, now you have two variables, in an isometric way if your function G has its L2 norm equal to 1. So in particular, what you're saying is that L2 of RD and L2 of R2D are like very similar through the short-time Fourier transform. And you can have, same as before, an inversion formula. And this is what it looks like. So now you can do some really good time frequency analysis. What you have is you begin with a signal, right? And you analyze it. You compute the spectrograph, for example, the short-time Fourier spectrogram, Fourier transform, the short-time Fourier transform. Then you process it. So you isolate the interesting parts of the modulus of the function. I mean, you have to look at the modulus so that you get something like interesting, like a spectrogram. But yeah, so you modify the function, your signal, through its spectrogram, and then this gives you another function, which you can then invert. Let's say bring back from L2 of R2D into an original function, which is going to be somewhat similar to what you started with. And yeah, so this would be, for example, the process. And this is exactly what I did this Saturday. So we were having dinner, and well, let me show you that part first. We were having dinner, and a friend was playing the guitar, and I was having some pretzels at the same time, and I recorded the thing. So in the original file, you can hear this. That's me, right? And so I wanted to get rid of this. Now I do mathematics. I'm not a signal analyst or anything, whatever they're called. So I tried to fix it by just keeping the harmonics, right? So this way, in that part where I take the byte. So what I'm doing there is basically trying to keep the sound of the guitar in the function, but get rid of the of me. And this is what it looks like. So it's a bit muffled, no, but you can clearly see that it's not there's not the munching sound. And also another way of maybe producing some modification of the function that you start with, it would be to focus just on what happens on a certain part of the spectrogram, right? So there's this tone that's called the Shepard tone, and it's like an overlapping of frequencies in which you always think that there's like the tone is going up, right? That's the impression that you get, but then it always remains in the spectrum of frequencies that you can hear, so it cannot be going up the whole time. And what it looks like is something like this. I think it's going up, and it is going up, but then you're starting to introduce new frequencies at the bottom. So when you isolate some of them, you get this. It's just one of them that's going up, and then the next one takes over, and so on and so on and so on. So this gives you like the information that, well, basically, this is, by the way, this is the signal that I showed the Fourier transform of before, and now it makes sense that it's got like a bit more of the frequencies accumulated on the low side of the spectrum. This is like more yellow than this part, and then it decays somewhat, and then like from here on, there's no more frequencies. But yeah, this is the what happens, no? So you can play it as long as you want. I mean, yeah. Anyway, I think the point got across. Okay, so we have another uncertainty principle on the short-time Fourier transform, which is basically the same as the uncertainty principles that we had. Does it work? Yeah. All right. Sorry. Yeah. So what Leib's uncertainty principle tells you is that no function can be like concentrated on small sets in the time frequency plane, regardless of which time frequency distribution you use. So the short time Fourier transform will be a time frequency distribution, but you can also use some other different distributions. You can change the window, and still you wouldn't get anywhere near what you want now, which is perfect time frequency resolution. But yeah, so that concludes the part with short time Fourier transform. Now there's an interesting tool that pops up in time frequency analysis, which is the Bargmann transform. And this basically allows you to take problems with the short-time Fourier transform, and it converts them into problems on like the Fock space, which is basically holomorphic functions in some L2 space, which we will see. And it comes from analyzing what the short-time Fourier transform looks like. So take a Gaussian window, right? Gaussians are the functions that minimize Heisenberg uncertainty, so it makes sense to take these windows. And rewrite, I don't know who came up with this, but like they rewrote the whole expression, and they arrived at something like this. And so this is the short-time Fourier transform of f with respect to this Gaussian window at x minus omega. So there's this slight modification. Anyway, and now what you can see here is that inside the integral you have x plus y I omega twice, and that looks a lot like a complex number. No? So you can take complex numbers, like put them in here, and then define the Bargmann transform like that. And it turns out that this really ugly expression turns into this when you define the Bargmann transform. And also note that here, for every set, we're integrating on t. So, I mean, this is going to be a nice function, and you will be able to differentiate under the integral sign. So, because, I mean, you look at the whole thing and it's a bit messy, but anyway. And this function has, or this transform has really interesting properties. So the first one being that it's in this L2 space that I was mentioning before, and it basically means that if you integrate the Bargmann transform squared with respect to that measure, so basically the measure is like multiplying the Lebesgue measure times e to the minus pi modulus of z squared, then you get precisely the L2 norm of f. So you see already that there's going to be some way of going from L2 to whatever this thing lands on. And BF is holomorphic every time f has polynomial growth. But the thing is, if f is in L2, then it will have decay. Like it won't be growing. So it will have polynomial growth in the sense that, yes, of course, you're going to dominate it every time by a polynomial. And so yeah, if you define the Fock space by just the entire functions that, so for a function to be holomorphic, it means that it's differentiable as a function from the complex numbers to the complex numbers, okay? Entire means that it's holomorphic in the whole domain, so in the complex numbers, C, D.
So what did you mean by f and L2 by the polynomial growth?
So the thing is, as long as f grows like a polynomial, so like t to the n for some n, you will get, with the Bargmann transform, you will get a holomorphic function. And since L2 functions cannot grow like crazy.
They can if they're in intervals. I mean, you can have some nasty.
Yeah, but I mean at infinity, if they imagine it's not bounded, right? Imagine at some point it's greater than some constant. Then in RD, the whole thing is like the measure of that set is going to be infinite. So I mean, at some like in a bounded, in a compact set, you can have weird things happening.
Like I was saying, you could have like very narrow spikes at which it's very large. I don't know how you define polynomial growth.
Yeah, okay. Polynomial growth means that you can uniformly bound it by a polynomial. So you cannot have those spikes. Maybe I should have been more concrete.
But then, so if it's in L2, it might not have polynomial growth.
Well, I mean, you cannot have those things happening like infinitely often.
But I mean, you could have spikes of exponential heights with they're exponentially narrow somehow, right? So that it's average.
Yeah. Okay. All right. Sorry.
I mean, we could discuss it.
Yeah. Okay. Maybe it's best to discuss it in APRO, but I think it doesn't work. Anyway, we will discuss it in APRO. Okay. So now it's a perfect match for the Bargmann transform, the Fock space, right? Because you land precisely in this space, and this space is actually a Hilbert space with a reproducing kernel, which is one thing that's really useful for the structure of the thing, anyway. And it's an isometry. So the Bargmann transform will land here, and really what you need to, like what you would ask for really hard right now, is for it to be surjective. Because if it was surjective, then like doing things with the short-time Fourier transform would be the same as doing things with the Bargmann transform. And the answer is yes, it's surjective, and problems in L2 with the short-time Fourier transform, you can deal with them as if they were problems with holomorphic functions in the Fock space, which are really very nice. I mean, it's much easier to work with those. And so this, for example, was used in 2021 by a couple of authors, which were asking themselves about the energy concentration of the short-time Fourier transform of a function, right? So if you have a set in the time frequency plane or in RD, and you integrate the modulus squared of a function over that set, that would be the energy. That's what we said before, right? So you can think of taking the supremum of all of these quantities over the function in L2, right? And this would be the energy that a set can accumulate at most, concentrate at most, like the maximum that you can have over of the energies of that set, right? So we call that the energy of the set. So what they proved was that this energy it's bounded above, and also that's what I think is the more important part, or like the key part, is that if this equality is achieved, then your domain has to be a ball, and up to a set of measure 0. So it has to be a ball, and the function has to be this kind of function, right? Which you don't have to remember, but just we will call this a Gaussian, although it's like sort of a Gaussian, but it has to be this. So anytime you have this kind of problem in which you have an inequality and you have a characterization of equality cases, you can ask for stability. But let's roughly, really fast look at the outline of the proof. So the proof basically follows the next step. So first of all, you use the Bargmann transform to turn this problem into an easier problem, and now you have a really happy Pikachu. And then you study the level sets of the functions that lie in the Fock space. So which are these? Well, I mean, this is what's in the integral of the norm of a function in the Fock space, but that's what you work with in the problem. But anyway, so you look at the level sets, and then you find the result eventually with some geometric measure theory and some other techniques. And then stability it tries to deal with the following question: if you have an inequality, right, with characterization of equality cases, and this inequality fails to be an equality for a function f and a domain or set omega, it fails to be an equality by a really small margin, then do you gain at least some knowledge on what these guys look like? Do they have to be close to what the objects that achieve equality look like? And the answer is, for example, for the isoperimetric inequality, yes. It tells you that the balls are the sets that have the best ratio perimeter to area, right? And like they are the minimizers. And you have stability. And here, well, we could try to prove something like that. And this is what I've been working on in the semester paper. My semester paper is sorry about that. But anyway, so you can measure maybe, for example, what would be the difference between a ball and this set omega by just taking the symmetric difference. So the part that's in one of them and not in the other, right? Union, the part that's in the other and not in the first one. And you take the volume and you quotient by the volume of the whole set, just so that you have a relative measure. And you take the ball that best approximates this set. And this is the failure of omega being a ball. And now for the function, you can just use the L2 norm of the function. So you would take the best, okay, you have an infimum here, but you would take the best phi that approximates f by just moving it around. And, or you could take the Bargmann transform norm since it's the same. And then you define how bad the inequality fails from being an inequality, right? Which is basically the right side of the inequality minus the left side of the inequality, and then you can quotient just to have a relative measure again. And so the idea would be that if this is small, then this is small, and this is small as well. So you can formulate this in this kind of result. So C of D and C prime of D are constants, which may depend on the dimension, and delta is the deficit that we looked at before, is how bad it fails, the equality, and alpha and beta are just some exponents that you may have. You may find that they occur. And this is what I've been spending my time on, and I haven't followed the probability course, and I regret that, but we have proved some sort of stability, so I'm happy. And so this concludes the talk. If you have any questions, you may ask them now or during the apéro. If they are long, maybe during the apéro. And that's it. I'm done.